So for the Q&A session, you can write down your questions, and the questions will be raised by the end of the presentation. And for those questions that are not addressed due to a time limit, we'll collect them and send them to the speaker later. Okay. So let's move back to today's talk. Today we have Professor Neepa Maitra from Rutgers University, and she grew up in New Zealand and finished her undergrad degree there at University of Otago. She then went to Harvard University for a PhD, where she studied the semi-classical techniques, particularly for classically forbidden processes with Rick Heller. And after a short postdoc with Professor Bill Miller at UC Berkeley, she entered the field of time-dependent density functional theory with Professor Kieran Burke at Rutgers University. She then joined the faculty at Hunter College in City University of New York for several years. And last year, she moved back to Rutgers University at Newark. And the research in her group centers around three aspects: functional development in time-dependent density functional theory, the exact factorization approach for coupled quantum subsystems, and very recently, Polaritonic chemistry. And today, Professor Maitra will give us a talk entitled Time-Dependent Potential Energy Services for Polaritonic Phenomena. With all introduction, let's move the stage to Professor Maitra. And Professor, you can start to share your screen. Okay.
Oh, okay.
Can you share your screen now?
Let's see. Ah, yes. Now I think I can. Okay. Let's see. It's working. Okay. Okay, great. Okay, yeah, well, thank you so much to Bo and Hoel and Wei and your research groups. You know, this is really a wonderful seminar series you set up, and so soon after the lockdown started due to COVID. I'm just impressed with the efficiency and also the success and how smoothly these run in such a short amount of time. So we're very lucky to have this series, not just for the high quality of the talks so far, but also really for the escape it offers us from the awful events occurring here in the United States. I feel like we're so preoccupied with them that we need to say something about this. It's really laid bare the racism and injustice throughout many systems here, and we desperately need a change of leadership in our country. It's been a bit hard to concentrate, actually. But now to the science. I'm not really an expert on polaritons. However, I've in fact learned a lot about the field of this very exciting new developments in the field from Nora Hoffman, who joined the our group at the time in New York as a PhD student about 3 years ago. She was on a fellowship from Hamburg, where she's officially a PhD student. And in fact, yesterday she just defended her thesis, so this was very exciting for us all. And due to her, our group kind of became interested and involved in some of these very interesting problems that happen when you're in the strong light matter coupling due to confinement. And what I'll talk about today is work with her and postdoc Lionel Lacombe. He's a postdoc in the group who actually works on almost everything that we do in the group. So, so the basic idea of what I'll tell you about is that we're applying somewhat of a new approach, or somewhat of a new approach, or a new way of viewing coupled quantum subsystems when we're particularly interested in one particular part of the one particular subsystem. So, and this is called the exact factorization approach. And let me maybe I begin first by showing you the kind of Hamiltonian that we're going to be looking at throughout, right? So this is actually the simplest, oops, I've lost my, here we go, sorry. This is the simplest Hamiltonian for systems of correlated nuclei, electrons, and photons. It's non-relativistic. I've neglected spin coupling, neglected any cavity losses. I'm making the dipole approximation in the length gauge, and I don't have any external fields, right? But even then, it's quite complicated, right? So we can break it up into several parts. There's the matter part, the photonic part, this photon-matter coupling, and a self-polarization term. So let me go through a little bit what we mean by these terms, although just to put everything on the first page here. So the matter part is the Born-Oppenheimer electron-nuclear potential. So these are the Coulomb interactions between electrons and nuclei, and the kinetic energy of the electrons and the kinetic energy of the nuclei. So we break it up like this. The photonic part, arising from these approximations made from QED, can be written in this form as a set of oscillators, harmonic oscillators, where we sum over the number of different modes or frequencies in cavity frequencies. And Q here, so we can kind of view this P as a kind of kinetic term, if you like, and this Q as this Q squared term as a harmonic oscillator. So the Q is technically related to the displacement field coordinate, where A and A dagger here are the creation and annihilation operators associated with that mode. Oops, sorry, there should not be a sum on alpha here, of course. Sorry about that. Okay, so these are this is the matter part, the photonic part, and now we have the photon-matter coupling, which from these approximations turns out to have a bilinear form. The dipole moment, the total dipole moment of the matter is coupled in a linear fashion to this displacement field coordinate Q through this coupling strength lambda alpha, and we've separated out an omega alpha here, and our Q has an omega alpha square root in the denominator, which means that lambda alpha, at least for 1D planar cavity, it actually has this form. X is the distance along the cavity. We'll be taking X to be 0 in most cases. In other words, we'll be considering molecules which are really, we consider large enough cavities that the molecule is kind of in the middle of the cavity at X equals 0. And so then the lambda alpha is actually about the same constant for each mode, right? Okay, so this is a simple model, if you like. Okay. And then we have this all-important self-polarization term. And why it's important, we'll come back to later in the talk. I guess there's also been some beautiful work from Angel Rubio's talk, from Angel Rubio's group, where we, oops, I seem to have lost. Okay, sorry, no, where we, where they have shown that without this term, you don't have a consistent ground state, right? So it's very important in certain cases. In fact, in some of the single mode problems I will be looking at, it has a negligible effect on the dynamics, but I'll come back to it at the end, right? So you can see that it looks like it involves only matter operators, right? It's only the dipole moment squared of the matter system. There's no Q here. However, of course, it's caused by the vacuum field fluctuations it's a dipole-dipole coupling from the matter due to the radiation field. Okay, so here's our Hamiltonian. Let me see. Oh, I see. Okay, sorry, I clicked somewhere strange. Okay, and then, of course, if we want to try to solve the problem, we might think, okay, I have to solve time-dependent Schrödinger's equation. And of course, if you try to do this for more than, one photon degree of freedom, one nuclear degree of freedom, one electronic degree of freedom, your computer explodes, or more, you actually have way too much information than you want, right? In a typical situation you might be interested in, for example, enhanced conductivity or something like this, then we really want to know about the electronic system. Or you might want to know about cavity modified chemical reactions, and you want to know where your ions are at the end of the day, right? So that means you really want to be focusing on the nuclear system. So this kind of raises the question, can we write down a time-dependent Schrödinger equation for each subsystem alone that describes the dynamics of that subsystem exactly, right? So we're just kind of focusing on one. Of course, if we could do this, then the exact potentials in such the Schrödinger equation have a really important and heavy role to play. They must exactly capture the coupling to all the other subsystems and any external fields, right? So this is a, this would be nice in a way, because then we could kind of understand and analyze and give insight from these potentials, and then possibly also, build practical methods based on, mixed quantum classical type methods based on this system. So this is the ultimate goal of the exact factorization approach. I'm going to show you that, in fact, this is possible to do. And then I'm just going to show you some of the things we've been exploring in its application to polaritonic chemistry. And then, point to, we're not yet at the point that we are currently, our group is not currently applying mixed quantum classical methods based on this approach to study realistic systems, but I think we're short down the road, actually. So I will, I'll show you, I'll point to some literature which suggests kind of good approximations based on this approach. So here's the outline. Okay, so I'll tell you first about the exact factorization approach, where in the first part I'm going to just think about correlated electron nuclear dynamics, as this is actually where the approach began. And then we extended it to include photons. And so in this part I will tell you about a model of cavity modified proton-coupled electron-transfer. And we will study the exact potential driving the nuclei in that case. We will also take a look at the exact potential driving the photons. And then I'll say just a couple of, I imagine I will be short of time here, so I'll just say a few words about treating many photon modes and these self-polarization modified surfaces. Okay. But for now, first we're going to forget about photons for a little bit and just think about coupled electron nuclear systems. Okay, so this approach, as the introduction was supposed to convey, it enables rigorous definitions of exact potentials acting on the electronic subsystem and nuclear subsystem. So now let's look at our molecular Hamiltonian. So we've just taken away all the photonic parts. And in fact, here I've added some kind of laser field or some external field that could be driving the electrons. External field could be driving the nuclei. Okay. And this Born-Oppenheimer Hamiltonian is the same as we just wrote, the kinetic energy of the electrons, and then the Coulomb interactions between electrons, nuclei, nuclei, and electron. And again, we're trying to find a way or a representation of our full electronic nuclear wave function. And so I'm sorry about the change in notation here. The double underline here means all electronic coordinates here, all nuclear coordinates here. Okay. In fact, it was shown by Jeffrey Hunter, back in 1975, that the exact solution of the Schrödinger equation can be actually uniquely factored in the following way. You can write it as a marginal amplitude multiplied by a conditional amplitude here. So what we do is we can identify the marginal amplitude as a nuclear wave function, because one can show that if you do this factorization, and we'll talk about this in the next slide as well. If you do this factorization, we find that the nuclear wave, the function the equation that this satisfies shows that this function here reproduces the exact nuclear density of the full electron nuclear wave function, as well as its current density. So in that sense, it's a bona fide wave function representing the nuclear system. And this is then a conditional electronic equation. So it looks a lot like a Born-Oppenheimer, doesn't it? But actually it's exact and it's time dependent. Now, this condition here, that the conditional electronic wave function, after you integrate over, if you square it and you integrate over all electronic coordinates, for every nuclear configuration and every point in time, it must integrate to 1, right? So it's really like a conditional probability, right? The amplitude, right? So this is a very crucial condition, because if it wasn't for this condition, this factorization would be trivial, or and definitely not unique, right? You could come up with any kind of factorization like this. In fact, it is this partial normalization condition that makes this a unique representation of the exact wave function. Okay, and so it's very interesting because the it looks very much like Born-Oppenheimer approximation, but actually it's not an approximation in fact at all. It's an exact representation of the wave function. One can prove this. Hunter has proven it for the time-independent case. There was some other papers also with Guidopoulos and Gross, and in this paper here with Hardy-Gross, who's really the I was just very lucky to be involved actually in this work with Ali Abedi and Hardy-Gross. They it was their what we showed here was that in fact this factorization is unique and exact, and that if you then ask yourself what these equations satisfy, what these forms, what these factors satisfy, you get a set of these coupled equations, right, shown here in the brackets. So let's take a look at these in a little bit of detail. If we first look at the nuclear equation, you can see that it has a Schrödinger equation form, right, with a kinetic energy term with a vector potential, and then the potential here involving the what we call here a scalar potential, the exact time-dependent potential energy surface, right? If we compare this with the Born-Oppenheimer approximation, you can see it has a similar kind of form, but it's completely different because, of course, these are exact potentials that reproduce the exact time-dependent wave function of the nuclei. So actually, if we look at what these are, these contain coupling to the electronic system in an exact fashion. If you look at the exact time-dependent potential, the form of this wave function here, you can see that it involves the electronic Hamiltonian, which I'll tell you about in a minute, minus ID by dt sandwiched in this in the conditional electronic wave function, and then this means averaged over or integrated over the little electronic coordinates, right? And so this gives you a potential energy surface which involves the electronic wave function here that the nuclei evolve in. And also the scalar potential here looks a lot like a sort of a Berry connection, but now our wave functions involved in this bracket here involve the exact conditional time-dependent wave function, not Born-Oppenheimer wave functions. And I'll come back to this in a minute because it's very interesting. Usually we think of Berry phases as arising from a separation of time scales, a fast time scale for the electronic and a slower time scale. And here we've made no such approximation, and we're getting, it seems like, if the curl of this was non-zero, then we would get a Berry phase as we rotate around, as we make a rotation in the configuration space around, for example, a conical intersection, if there was one. I'll come back.
Professor?
Yes.
Sorry to interrupt. There's one question.
Sure.
Hello, can talk.
Oh, hi, Neepa. So I just have a naive question. So from these two coupled equations, so if you which are the approximations that you need to make to really, say, reduce to the bare bones, like the textbook Born-Oppenheimer approximation? So for example, like here, everything depends on time, both the potential energy surface and the Berry connection, but normally we are used to it not being time dependent. So can you comment a little bit more on, if I have a separation of timescales, can I reduce it to like what we know from textbook?
Yeah, sure. It's a good question. So actually, if we want to, in fact, there's a paper of Federica Agostini and Florian Eich, who have shown that as you take these equations and you take the large mass limit, so you take big M going to infinity, then you have to be a little bit careful because there's some gradients here, and you're pulling down factors of momentum, right, which involve mass and so on, right? But you can show that you recover the Born-Oppenheimer approximation. In this case, then I guess in some sense you would assert, in order to get rid of the time dependence, I have to revisit what they do there. But I think what you'd have to do is assert that you begin in an eigenstate, right, and then show that you just evolve as e to the I epsilon r.
In an eigenstate of the
I guess Yeah. So maybe I should put it another way too. I mean, these are the time-dependent exact factorization equations. One can also show, in fact, the work of Hunter was with a time-independent case. So you looked at stationary states, right? And in fact, yeah, I should revisit the paper of Florian and Federica, because it could be that they also looked at just the static case there.
Okay.
So you can, in fact, also do a static. You can look at these equations for a static problem, right? And then ask yourself, well, if I had an eigenstate of, my full wave function here, I'm wanting to find H psi equals E psi as the molecular wave function, electron nuclear coupled one. If I can I factorize it? And yes, you can, and you can have this, and then you would get an exact form for the time independent. For the static one, it wouldn't be Born-Oppenheimer, right? Because these potentials would be different. And then you wouldn't have, it would look similar to this. There's no d by dt, obviously. There's an epsilon, nothing's time dependent, right? And you can show that in that static picture, in the static exact factorization, you reduce to Born-Oppenheimer.
Thank you very much.
Yeah, sure. Yeah. Okay. Yeah, so look, we have a Schrödinger equation for one of our subsystems, but what about our other subsystem? So our other subsystem, and sorry, I put in the red boxes here are kind of the new terms, right? Or the terms that involve the couplings, I should say, not new terms, involve the couplings to the other system, right? The correlation. So you can see then in this electronic equation here, this operator, unfortunately, this is not at all a Schrödinger equation, right? It doesn't have the form of kinetic plus potential. It has these funny operators here where, okay, so this electronic part, it depends on the nuclear wave function, which we might expect, right? However, you can also see this operator here that it acts on the parametric dependence of the electronic wave function, right? So this is a very unusual operator. And it's a bit of a troublemaker, actually, if you try to self-consistently solve these equations. Maybe I'll say a little bit about that. But the point is that, okay, so the point is that, we now have a representation of the exact wave function as a single product. And these are the exact equations that those two factors satisfy. I mentioned before that it's unique up to a gauge-like transformation. In fact, you can multiply the electronic part by purely purely nuclear coordinate-dependent phase and time, and the nuclear part by the opposite phase. Obviously, the product of this is the same as the product of that. And if you actually work through the equations and see what happens, you find a very nice reflection of a gauge-like transformation with these potentials A and epsilon, right? The equations are completely invariant, form invariant, provided you do this gauge transformation according to this phase that you multiplied by. And this then raises the question, going back to this question of, Berry connections, do they appear just in the limit that, you have infinite nuclear mass, or in other words, in the limit that you have a time separation, a real time separation between slow and fast, or are they still there even in the exact case, right? And in fact, people have looked at this question, and the answer is a bit subtle. I will talk to you about that shortly. Of course, in order to be able to gauge the vector potential A away, and in many cases, in the examples I will show you, I gauge it away, mostly because I'm dealing in a case where I have one dimension, and I can always then transform a vector potential into a scalar potential. Okay, so the other point about this is that it provides a rigorous starting point for approximations and insight into traditional methods. And I just put up here some literature on different aspects of exact factorization. I mentioned the geometric phase. In some of these works, they showed that, in fact, the curl of A, it becomes, or there becomes like a conical intersection, if you like, only in the limit that the mass goes to infinity, and in certain systems. In other systems where there's a symmetry, where this conical intersection of the degeneracies arising from the symmetry, you find a geometric phase rather than a topological phase. So there's a lot of work being done here in this paper here. They looked at dynamics through a conical intersection, not just the static surfaces. The mixed quantum classical methods based on exact factorization, a few have been developed very recently and successfully applied to look at, to sort of overcome, the hope is that we can overcome some of the problems that surface hopping has, for example, involving decoherence. And one can add sort of ad hoc decoherence corrections, somewhat ad hoc, some are very well motivated, but it would be nice to be able to have something where one derives a decoherence correction. And for example, in this work by Sim-Kyu Min's group, they have done this, and they have a very practical algorithm where is like a surface hopping method that's based on exact factorization. In these papers here, they have what's called CTMQC. It's slightly more complicated, slightly more numerically involved method that also includes decoherence. I mentioned that if you actually want to try to solve the exact factorizations as a set of coupled equations, you can run into trouble. And there's this paper that we looked at here, with very somewhat incomplete answers on the stability, but it raises issues about, you probably don't want to do this. It's probably more simple just to solve the full equations if you can, right? But that's kind of not the full Schrödinger equation if you can. But that's kind of, again, not the point of the exact factorization equations. It's more to give insight, as we are going to see it with the Polaritonic case, and also then to build mixed quantum classical methods. So I've mentioned a number of different directions that the subfield has gone into, including sort of embedding methods that Lionel Lacombe has developed very recently for strongly correlated systems, where we factorize in Fock space within the electronic system itself. Density functionalizations of this, getting beyond Born-Oppenheimer functionals, right? So, yeah, I mean, there's more beyond this. I just wanted to sort of illustrate the spectrum here. But what we're going to look at in the remainder of the talk is extending exact factorization now to include photons. And I'll just double check the time. Okay. So again, we want to now enlarge our Hamiltonian now to include the photonic degrees of freedom, right? So now this is the Hamiltonian I showed on the first slide, with the photonic part and the photon matter coupling now added, and the self-polarization term, right? So this is just what we had before. Okay, and now we have, instead of just little r and big R, the electronics and nuclear coordinates, we also have a Q for the photonic degrees of freedom, okay? And so we can imagine various different kinds of factorizations that we could do. First, we could say, well, let's separate out the margin. Let's take the marginal. Remember, the marginal is the one that has the nice Schrödinger equation, right? So if we want to if the subsystem that we're really interested in is the photonic degree of freedom, then we'd like to have a Schrödinger equation for the photonic degree of freedom. And so then we would choose this Q to be the marginal coordinate. And then our conditional coordinate is a conditional on Q, and it's a function of the matter system, right? Then we could say, well, I'm actually more interested in, looking at cavity modified chemical reactions. And then in that case, I might be more interested in having an equation for my nuclear system, right? A Schrödinger equation with potentials that I can take gradients of and look at forces, which are then going to drive my nuclear system in a mixed quantum classical approach, for example, using the potentials that are coming from some approximation to the equation for the other part, right? And so then we would use this factorization because we want the marginal to involve the nuclear coordinates, or if we want the marginal to involve the electronic, right? And so, in fact, all of these factorizations have to somewhat extent been studied, at least just really sort of in a preliminary way, right? This has been 1 or 2 studies on each, right? So, in fact, this was the one that we first looked at when, sort of early on when Nora joined the group, and I was learning about the Polaritonic work with this joint with Heiko Appel and, oops, this should be an A, Ángel Rubio. And so here, where we want a Schrödinger equation for the photonic system, and what we're going to see, and I'll talk about this shortly, is we find corrections due to the quadratic form, corrections to the quadratic form of the light part of the Hamiltonian due to matter-photon coupling. In this part here, we can also look at, if, as we mentioned, we want to get a Schrödinger equation for the nuclear system. And here we find an exact potential driving nuclei when coupled to electrons and photons. And I will actually begin by talking about this work here, which was done with Lionel and Nora. And in fact, Ali Abedi and Elham Khosravi and Ilya Tokatli also looked at electron-photon factorization without a nuclear coordinate here. But they, and they looked at, sort of the effect of photonic degrees of freedom on in an electronic double well. So this was also being studied, right? Okay, so I'm going to begin by looking at showing you some of these potentials in a case of cavity modified chemistry. And so first, let's ask ourselves, well, what do we usually do for a molecule in a cavity? In other words,
Professor?
Yes.
There's one more question.
Sure.
Matt, you can talk.
Hi, I just want to ask a clarifying question. So again, in this exact factorization scheme, you can treat any of them as a quote unquote like slow coordinate, right? So
right, yeah. Well, I would call it the marginal coordinate.
Coordinate.
Yeah, yeah. Uh-huh.
So I guess so in the previous case, right? Where you just had electrons and nuclei, you could have done the same thing by treating the electronic
excellent question. Yeah.
As the marginal case, right?
Yeah,
marginal
very. Yeah, great question. Yeah, in fact, so this is the reverse factorization.
Okay,
so if you're interested in that, yeah. So actually, we looked at this for certain cases of sort of like if we're interested in sort of electron localization, like control of electron localization with a field, or we looked at charge resonance and enhanced ionization phenomena in this paper here. And there, if we're interested primarily in what the electronic system is doing, then we want to have a Schrödinger equation with potentials that we can understand and interpret for the electronic system. And that is, as you point out, that's what we want to do there. We want to have the electronic system as the marginal. Yeah.
Okay, thank you so much.
Yeah, thank you. Okay, good. Okay, so returning to the Polaritonic system. So the potential energies. So first we might ask, well, I have a molecule in the cavity. What first plays the role of static Born-Oppenheimer surfaces? Just kind of for a backdrop, a sort of a static backdrop, and then we're going to look at our time-dependent potential energy surface on top of that, right? So, and you may know this much better than I do, but so there's polaritonic surfaces where you take your full Hamiltonian, subtract the nuclear kinetic energy, and diagonalize that. This gives you a set of energy surfaces in the nuclear coordinate, and these are called polaritonic. So you can see here that photons and electrons are treated quantum mechanically at the same footing, right? You can also, however, think, well, and for different purposes, as explained in these two papers, they have different uses or give different insights. Cavity Born-Oppenheimer surfaces, where you treat the photons on the same footing as the nuclei. Okay, so then you might be you diagonalize the Hamiltonian minus the nuclear kinetic energy minus the photonic kinetic energy, that the d squared by dq squared, or the p squared term in our Hamiltonian, and this gives then surfaces, two-dimensional if you like, or r and q dimensional surfaces, right? Cavity Born-Oppenheimer. In fact, for the purposes of the system we're looking at, this forms a particularly useful backdrop to the exact time-dependent potential energy surface, as we're going to see. So firstly, let's look at the model, and then we'll return to those surfaces. So here, we're going to look at a model of proton-coupled electron transfer. It's one electron and one nucleus and one D. So you can't, okay, you could complain to me about the reality of the model. Of course, it's not real, but it's very instructive. So we have a nuclear coordinate here. These are the Born-Oppenheimer surfaces. There's the ground Born-Oppenheimer surface, first excited. These are the four lowest. And you can see that there's an avoided crossing over here. If we ask ourselves, what are the Born-Oppenheimer electronic states associated with these surfaces look like? What do they look like? Well, in fact, I'm going to end up starting a wave packet up here. And in other words, I'm going to start a Gaussian nuclear wave packet on the first excited surface. And so therefore I want to know what my electronic state might look like there. And you can, and it's shown here, and you can see that it sort of is peaked more to the left, right? So you have an electron kind of on the left of little r, right? Now, as you imagine, if we start here and we run the dynamics, the nuclei is going to slide down this potential energy surface, encounter this avoided crossing, and it could split. It might split, some of it will get transferred to the lower surface, and some of it will get transferred to the upper surface. So we then might ask ourselves, well, what is the electronic character of the states, Born-Oppenheimer states associated with these two surfaces? The lower one, you can see, represents an electron transfer, because the electron start off more on the left here, the black curve here, and over here, after the proton has transferred, the electron black wave function is more on the right. Whereas if it remains on the upper surface, for example, it's just moving very, very slowly somehow, then, you know, if it will not do an electron transfer, right? So this is why this whole system is called a model of proton-coupled electron transfer. The black here is the cavity-free results given of the dipole, right? So you can see that if we start here, the nuclei is the dashed curve here. The black is hiding under the orange, actually. Sorry, the nuclei is here. So start at -4 and it kind of moves over here. And then it starts to reflect right over here. Whereas the electronic, it's this starts at little r equals -6 and it transfers this in probability transfer. What I've drawn in red and orange now is we put this in a cavity resonant with this frequency here, with this initial electronic excitation. And you can see that you get a suppression of both dipoles. In particular, you get a suppression of the electron transfer. And that's the red curve shown. This is for when you're inside a cavity with a coupling strength of 0.005. If I reduce the coupling strength to 0.001, you see that, you know, the light matter coupling is not that strong, and you basically get the outside cavity result. Okay, so this makes a difference how big the coupling is, of course. But now we might ask, well, can we now plot these polaritonic surfaces in these two cases, and will they be able to tell us the distinction that we're seeing here? So here are the polaritonic surfaces. In the solid purpley line here is the weaker coupling, and the light the 0.001. And the light blue dashed is the 0.005, right? And really, to the eye, they look about identical, right? So you see the ground state is basically the Born-Oppenheimer, right? So we're coupling the resonant mode. We have a single mode in the cavity of this frequency here, 0.1. So not surprisingly, a state which looks kind of like this state plus 0.1, which kind of looks like this, right? But then there's interactions with the other surfaces, right? These now come into play. So you have many more surfaces. This also shows you, so you have many more surfaces once you do the Polaritonic thing, because you have Born-Oppenheimer plus n photons, and also you have many more crossings, which kind of dooms surface hopping methods without decoherence, because it's very, very difficult to, you want to, anytime after a crossing, surface hopping ends up overcohering your system, and you run into problems, right? So we need sort of a new mixed quantum classical kind of method for these problems, right? So the hope is the exact factorization based ones will be helpful, and I'll say a bit more about that. Okay, so let's see. Okay, so it's very difficult to see just staring at these static polaritonic surfaces that you get this difference in dynamics. And yeah, so instead, so here, let's just have a look at the movies. So let's just look first, please, at the densities. Please ignore this. This is just a backdrop, the blue for the polaritonic surfaces. This, in fact, the messy graphs are they look messy right now, they won't soon, but they are the exact time-dependent potential energy surface, but we'll study that in more detail in a minute. First, let's just focus on the densities. So the black is cavity-free, and the red is inside the cavity with a stronger coupling. So at the beginning, they travel a little bit together, but you can see already here that the black is moving on ahead. The red is slowing down, right? The inside cavity result, right? And you can see then that now we're approaching the avoided crossing. We're about to hit the avoided crossing, at least the leading edge of the packet's about to hit the avoided crossing of the electron nuclear system. and this will be about to split, as we see. And you see that the in cavity, a part of the packet got left behind, ended up emitting some photon, right? And whereas the red, the part that made it to the avoided crossing splits in a kind of a similar way, actually, to the field, the cavity free, and then it reflects. Okay, so first we've seen that the polaritonic surfaces tell us really very little. Of course, we need to account for coupling, right? The non-adiabatic couplings between the polaritonic surfaces, for example, as Mukamel has discussed, in order to predict the dynamics, right? But just staring at the polaritonic surfaces is not so useful. But what we're going to argue or show here is the staring at the exact time-dependent potential energy surface, it correlates directly with the nuclear wave packet dynamics. So at early times, you can see that, and here we just eliminated the noisy parts, right? So, and of course it gets noisy because finding this is kind of an inversion problem. So in regions of low density, you get noise, right? But in regions of low density, we're not very interested anyway. And so here we have the nuclear density initially, right? And you can see at early times that you get this kind of gentle turn on the left side of the potential energy surface, which is kind of slowing down, if you like, the left part of the nuclear density, right? And whereas the right part is moving ahead. And this turn, or this gentle change in slopes resolves into a more strong change in slopes over time. And you can see that it's going to make the nuclear wave packet associated with the left, on the left associated with this part, move to the left, and the nuclear wave packet associated with this part, on the right, move to the right. And that's exactly what we see happening, causing the splitting, causing the suppression of the proton-coupled electron transfer, simply because less of this nuclear density has reached the electron-nuclear avoided crossing, which is where the transfer to the lower state occurs in the lower Born-Oppenheimer state. And so, and you can see also that what's actually going on is that there's a photon emitted in the early stages, right? So we can see, this is probably not surprising that this happens, right? But what we would like to emphasize here is the time-dependent potential energy surface is very is illustrating, right? Even if we didn't know what was going on, we can predict sort of the dynamics of the nuclear density from the time-dependent potential energy surface. Or maybe predict is too strong, but maybe I should say, well, it correlates exactly with that dynamics. Okay, so taking a slightly closer look here. So this time-dependent potential energy surface has different components. Let me just check the time. I guess I shouldn't take too much time. I just wanted to, I guess I can point to the reference and just point out here that, you know, at early times, it kind of, it's reflecting sort of photon matter correlation, because you can see that the light blue are the static polaritonic surfaces. The red is the, I guess, oh, sorry, but yeah, the red is the exact time potential energy surface, and the dark blue dashed is this weighted polaritonic component. So you can divide up, you can interpret this in different ways and look at kinetic components, gauge-dependent components, and this is kind of the bulk of the component in some sense. And you can see that the photon matter correlation is reflected in the sense that the part of the wave packet on the left is associated with a different photonic or polaritonic surface, electron photon system than the right part, right? So you can see that correlation in real space, if you like. And it's another interesting point, which also showed up with these studies of the exact surfaces without the cavity, is that the gauge-dependent part tends to have each time that we have a transition between, you know, and here on the left, we're on the third polaritonic surface, which has a character of Born-Oppenheimer plus 1 photon. On the right, we're on the excited electronic surface and 0 photons, and there's a transition down, right? And the gauge-dependent term tends to have a sort of opposing transition, such that the overall potential energy surface, once you add these together, is much smoother, right? The kinetic term is very small here because the nuclear mass is much larger than the rest. And so actually, the physics behind this is that it's kind of corresponds to kind of a velocity adjustment, if you like, in the sense that if we're dropping over here, if trajectories, if you like, or if we think of it in a trajectory picture, if we're dropping to a lower surface here in the electronic photonic part, the nuclear system has gained energy, right? And so this is kind of reflecting this gain in energy, right? So this, in some sense, can be interpreted in this way. Okay, so maybe I should, in the interest of time, I'll just show you this movie we can watch as a function of time. And these movies are also available with the PRL. So if you look at the supplementary, you can sort of watch as a function of time what happens. And in particular, you know, for example, you get this correlation happening at the end, near the end, where you have these three parts to your nuclear wave packet, you know, and they're on three different surfaces, right? So this is the exact, or the weighted Polaritonic part of the exact surface. And you can see it's bridging here, where on the third Polaritonic surface here, and so this is the surface is associated with one photon and the ground electronic state. This is associated with the upper 0 photons, but in the upper state, and this is again 0 photons, but in the lower state, right? So this is, you know, it's nice to see the physics of the problem here. Okay, I will skip that movie. And so I guess I should try to finish. I should try and finish up like in a couple minutes or something, right? Probably, or okay. Well, let me just try. So so then we could look at also the time-dependent potential driving the photons, and the motivation for this is the fact that photonic parts of the Hamiltonian are harmonic, and they have a bilinear coupling. And sort of known from sort of semi-classical theory that quasi-classical sort of Wigner dynamics or multi-trajectory Ehrenfest methods, when you have quadratic Hamiltonians, becomes exact as long as you sample the initial state, Gaussian initial state correctly. But if we look at this problem and we then say, well, let's try to do multi-trajectory Ehrenfest for the photonic part and compare it to the exact and compare it to cavity-free, and also compare it to a multi-trajectory Ehrenfest for photons and nuclei. This light blue, we don't expect to work very well because we all know that Ehrenfest for nuclear electron-nuclear problems near avoided crossings don't get the branching, right? So this is why it doesn't work very well. But you can see with the dark blue, which is just doing Ehrenfest for photons, but treating the nuclei and the electronic, nuclear and electronic system exactly, coupled to Ehrenfest classical photons, you see that we're getting some of the dynamics, right? We're getting, you know, we are getting the splitting of the nuclear wave packet, we're getting photons generated, we're getting some suppression of the dipole and so on compared to the cavity-free case, but it's not exact. The dark blue is not on top of the black. And in particular, we're getting an underestimate of the photon number. And so this suggests then the exact potential driving the photonic system is not harmonic, which raised the question, well, what is it? And so then, of course, we want to find it with the exact factorization. We already went through this, right? We look at this factorization and let's see what it looks like. So in fact, we had done this problem before we did the other one. So this was our first problem that we looked at when we looked at exact factorization for polaritonic systems. And so the system is simpler. We just took a two-level system, one mode, a very simple model here. This is a very simple model, right? And here are the let me show you what these would be the harmonic potentials of the ground and first excited photonic state, right? But let me show you how the red here, so where's my red? Yeah, the red here is the exact time-dependent potential energy surface driving the photons, and you can see that it becomes very rapidly anharmonic. In particular, at large Q, it becomes, oops, sorry, let me just try again. It sort of falls away from its initial shape. I don't know where is it? Oh yeah, here. At large Q, dropping down, widening quite quickly, and you'll see that a barrier develops here. And we can understand why this happens from the form of the Hamiltonian, and some analysis is written here. But for the purposes of the photon number, what this means is that, of course, the distribution, the width of the distribution is related in some sense to Q squared, which is related in some sense to the photon number, right? So you can see that these features are kind of pushing the the photonic density out to larger photon numbers. And so, and this, and the Ehrenfest, where you just have an average-like potential between the harmonics, you completely miss these features, and therefore you underestimate the photon number. So we can kind of understand those results from here. Okay. Maybe should I stop now, Bo, or shall I just, because this is another section, or should I keep going? I'm just a bit concerned because it's 12:53 already.
You actually have questions.
Okay, so I should stop, or?
No, this is a question in the middle, so you can ask.
Yeah. So hello, I have a question about the figure you just showed in the last slide.
Yeah.
Yeah. So I see what's going on, and at the point where the Q coordinate is 0, you have like a peak, and then you have like a minima around it. Probably due to strong coupling. But if you have ultra strong coupling, and if you add the self-dipole term, wouldn't you kind of remove a little bit of that effect?
Well, this is a good question. I think in general you might. However, for the two-level system, you can show that this is you can show that the dipole there's no self-polarization term, like it goes to 0. There's some, I guess, I don't think maybe we don't discuss it here. There's some work from Uncle Rubio's group for the two-level system with one single photon mode. There's the self-polarization term is, I think, strictly 0. Yeah. But in general, then there will be some effects from that. That's true.
Okay, thank you.
Yeah, thank you. Okay.
Maybe you can just spend a couple minutes to quickly go through it.
Oh, okay.
I didn't see a lot of questions actually, so maybe we still have some time.
Okay, great. Yeah. Okay, so right. So we could then think, if we're modeling real systems, we have many degrees of freedoms, and we clearly won't be able to find the exact time-dependent potential energy surfaces in those cases. But instead, as we mentioned, we can use either the surface hopping exact factorization or CTMQC, the references given on the earlier slides. These mixed quantum classical methods we need to adapt to include photons, and this is somewhat work in progress. I'm not going to show you results from that, but we can actually get some insight from, in fact, looking at self-polarization, looking at the sort of matter part of our full Hamiltonian. So here's our full Hamiltonian again. And on the left, I've separated all the terms in the full Hamiltonian that just depend on matter operators, right? So all the Q's and P's and so on, little P's and Q's, they're on this side, right? And all the matter part only, purely matter part is here. So the self-polarization term is part of this. Now,
Professor?
Yes.
We have one more question.
Right.
Okay, Lord. Oh, never mind.
Oh, never. Okay. All right. Okay. Thanks. Yeah. Okay. So we have then. So the thing is that normally for sort of lambda small, this goes like lambda squared. This goes like lambda, right? So this is often, especially for single mode cases, has no effect on the dynamics, and the results that I showed you before, we looked at including or not including this term, and it had no effect for one mode. However, as you increase the number of modes, you can see that this term becomes more and more important because you're summing over the number of modes. And in fact, and it's quite interesting because it's also independent of the frequency of the modes, right? So we thought, well, let's take a look at, as a kind of sneak preview on if we have many photon modes in the cavity, what's going to happen to the dynamics. We could look at surfaces which we call self-polarization modified Born-Oppenheimer surfaces. And basically it's the Born-Oppenheimer Hamiltonian plus this VSP, that's all it is. So you just add these two terms together and you diagonalize, and that forms these static surfaces, right? So we believe that this should be the right backdrop when we eventually will do a, look at or consider time-dependent surfaces for when we have many photon modes, right? Now, in the one mode case, we found polaritonic surfaces are kind of the best static choice for the backdrop for the time-dependent potential energy surfaces. They look kind of like Born-Oppenheimer plus n photon away from interaction regions. The many mode case, we now want to replace this with SPBO surfaces, right? The self-polarization modified ones. And then we would then couple them through VPM to get the self-polarization polaritonic ones, which would be important. But you can see that as the number of photon modes grow, and again, it doesn't matter what the frequencies are, well, with the approximations, I shouldn't say that, with the approximation that the lambda alpha is constant, right? With that Hamiltonian I showed you earlier, assuming that our molecules in the middle of the cavity and the sign function is basically 1 for all modes, right? Then you can see that the dynamics will be very, very different when you have 400 modes than if you have a single mode and even this too, right? Because we start here and the slope is very different. In fact, what we found, and you can check this result here for this paper here, it's on the archive, it's being reviewed, that, you know, that you get a suppression, complete suppression of the proton-coupled electron transfer in this particular situation. Okay, so maybe I won't need to cover the summary. Let me just thank Joel and Wei and their research groups for this. I want to thank Nora, this is her PhD from yesterday, Lionel. And the group at now Rutgers Newark, and Patricia, she's actually working on exact factorization methods for real systems, like you know, applying mixed quantum classical methods to this, to the electron nuclear problem. Philip and Bart are undergraduates at Hunter, actually, who have been taking on a piece of the Polaritonic problem, more analyzing the states. And Davoud is a PhD student working on TD-DFT. Thank you all for listening. Sorry for running over.
Okay, thank you. So we have a couple of questions. I'll allow them to talk one by one.
Okay, thanks.
Okay, Raphael can talk.
Hello, Neepa. Thank you for the very interesting talk.
Okay.
So I'm wondering on the last part of your talk. So in the last slide that you showed with the self-polarization, the dynamics, including the self-polarization.
Yeah.
So in your numerical calculations, so it seems that you stopped at 400 modes.
Yeah.
So
yeah.
does that calculation converge to anything or anything physically meaningful if you take the number of modes to be much larger than that?
No, it's a very good question, right? So I guess the thing is that we, so also one might wonder, how on earth did we do the calculation with 400 modes? So Nora, this is Nora's work she has a method called multi-trajectory Ehrenfest for these photonic degrees of freedom. And so she was able to run, so I guess running more than 400 modes is difficult. Well, she can do it. It would take longer on the machine. I guess the question also is, you know, how many modes are important in the cavity, right? So, well, I guess, you know, when I think it's a good question. I think we need to look further at the question. I mean, at doing more. Of course, when a question is, and something that we also need to look at is what we're doing physically with the system when we add more modes. Are we keeping the dimension the same of the cavity, like the length, and just adding more, right? And then, or are we having a larger cavity and the frequency range is smaller, right? Or compared to keep the number of modes fixed. Now, of course, from the self-polarization point of view, it actually doesn't matter apart from this issue within the assumption that lambda alpha is constant. But for the other terms, of course, it would matter. The coupling, once we add the VPM, the coupling between the photon and the matter, and turn these into polaritonic surfaces, we're going to, you know, how they couple will depend intimately on the length of the cavity and the mode spacing, right? Because it will depend on how much overlap there are between sort of n photon plus this surface and n photon plus this surface. So yeah, so I think it's a good question, and I don't have a clear answer right now. Yeah.
Sure. Thank you for the answer.
Mm.
Okay, so next.
Yes, hi. Thank you very much for the talk. The question is, how would you go about including relaxation terms in the dynamics of your Hamiltonian?
Yeah, that's a very good question. Actually, I haven't mentioned anything to do with any cavity losses, anything like this. So this, yeah, then I guess, in fact, if we think about the exact factorization approach, generally, you know, we're assuming a Hamiltonian system. So we're really assuming a closed system because we're writing down a wave function. So in the case where we have cavity losses, I guess we could try to do, you know, extend this somehow to a density matrix. I think it's difficult. I know that Federica Agostini has been thinking about this for the electron nuclear case. The equations become sort of, I don't know how tractable they are right now, right? I don't think, I think it was difficult to do. But yeah, so then we have somewhat of an open system, and then the question is, what do we do with the factorization? So yeah, I don't know.
Okay, thank you.
Yeah, thanks.
Thank you. Hi, this is Wei. Very nice work. So I have two questions. So the first question is from your potential energy surface of the proton. It seems like because you would always add more surfaces to diverge it from the right trajectory for charge transfer. Is it general to say that then in proton usually you would always expect to suppress the reaction other than promote it, because that is fundamentally always the case, and people are very curious about if we can actually promote a reaction rate. And then my second question is like how well that your method can be extended to vibrational strong coupling, and say if you couple a vibrational mode to the cavity, would you also expect to change the reaction, see a change of reaction on your surface?
Yeah, no, these are very relevant questions. Yes, no, so for the last part, yes, we would definitely, and we actually began a little bit to look at this and then got distracted. So yes, we would, for vibrational strong coupling, yeah, you would end up distorting this shape quite a bit, and actually, depending on the self-polarization term, actually, you can find it can play an important role in the distortion actually as well. So yes, but indeed it should reflect the exact surface will again reflect the vibrational strong coupling effect. As for the question about enhancement of the electron transfer, it's very interesting. I think, yeah, so we can see, you know, we can see from the exact surface here, it's quite clear why we're getting a suppression each time, and it's, you know, with the photon emission, I suppose. I guess the question is whether the, you know, we end up enabling meeting other surfaces in which maybe later on there's more of a slope downwards that wouldn't be accessed. You know what I mean? Like if you end up, if somehow the dynamics encounters a surface, makes a transition to another surface enabled by the surface, by the strong light matter coupling, where at another part in the dynamics that surface ends up, you know, having a large slope to the right or whatever, then perhaps you could get an enhancement. It's not clear to me yet that you would always get suppression, but yeah, maybe I need to read more as well.
Yeah, that makes sense. Thank you so much.
Yeah, thank you.
Hello, can you hear me?
Yes, I can. Mm-hmm.
Yeah, great. So I have a question actually about the last part of your talk when you were talking about the basically dipole squared term, right? And you said that you implemented that for cavities with large number of modes, but even if you have like the molecule in vacuum, so the vacuum has also like a continuum of transverse electromagnetic modes in principle, right? Yes. So I'm wondering, like, what would be the effect of this continuum of electromagnetic modes, and do you take it into account in your calculations?
Yeah, no. So this is a good question. In fact, we you know, we found that the one effect of having a quasi-continuum of these states is that when you have these many modes, is that we we get the Lamb shifts. So all the and so we get this kind of, I mean, maybe I should call it a Lamb-like shift, right? But certainly in the vacuum and outside the cavity it would be a Lamb shift. So, but we're also seeing these shifts in the expected frequencies that we're seeing in like you can spectrally decompose like a photon number like quantity over frequency range, and we see that as the number of photons increases, we get a shift in this frequency. You know, I being relatively new to the field, I realize that there's a lot that I actually still need to understand better. But we are seeing these effects and sort of interpretation and convergence and these questions and depth spacings are things that we need to understand better, actually. But yeah, we do see this.
Thank you.
Yeah, thank you.
Okay, maybe one last question.
Hi, Neepa. Thank you for very nice talk. So, can you go back to your slide where you show the exact potential energy surfaces? Yeah, here. Okay. The next slide, if possible.
The next slide is instructive. Yeah.
Okay. So you were saying, okay. So I mean, normally you would get these like surface hopping type structure in the blue. In the blue thing, because that's kind of like what we're used to in the regular Born-Oppenheimer ideas, right? But then you say that gets compensated by this term that is due to the derivative in time. Is that what you're saying?
Yeah, well, it's not completely compensated. No, so firstly, just to make a point about surface hopping, it's actually, in some sense, it looks like a surface hopping, but actually the way it operates is very different, even the dark blue term. Because, for example, in the surface hopping, you come along here and you hop right near the intersection, right? You would hop kind of there, you know, at the intersection or close to it. But actually, if you look here, at the early times, in fact, at early times, you know, we're right near the intersection here, it looks more diabatic. The exact surface looks more diabatic. And in fact, the suppression effect, like this part of the wave packet actually, you know, being left behind, happens sort of almost in the early stages, really, or as the early stages before that you, before you get this, you know, the separation into third polaritonic and then second polaritonic. So yeah, even though I mean we're actually heartened to see aspects of surface hopping reproduced, because we, you know, it's a beautiful algorithm actually, even if one can't derive it. But you know, but there are differences, and I think these differences are important in order to you know, because it's the exact thing for one thing, but also the subtleties of how you're hopping the surface, or, you know, going from one to the other. Now, so also in surface hopping, to do with the green compensation, in surface hopping, we also have the effect that, which is, and it, again, is not derivable, but you put it in by hand, that you, when you make a hop, you adjust the velocity of the nuclei, right? So because you look at the energy before, you know, either it's along the non-adiabatic coupling vector, but you adjust the velocity to sort of make sure that your nuclear trajectory, or, you know, so you compensate the change in energy, right? So this green is basically doing that, right? Because you're kind of compensating the drop, and so you're getting a drop here in the energy of the sort of polaritonic, like the electron photon system, from here to here, but the nuclear energy goes up by about that same amount, not completely, but roughly. So it sort of partly compensates that. And then if you look at the slopes on either side of this junction, this slope is identical with this. Like, this is piecewise flat, more or less, right? And so the actual forces are the same, but it's just that it's subtly different in this region here. So this is where, you know, sort of insights and into surface hopping and insights.
So this lack of full compensation, it's really because you are kind of changing to a different potential energy surface shape. Is that the way intuitively I should think about it, or?
Yeah, I think so. You're changing. I think you can. So actually, we're also analyzing, because so if you look here, for example, you see that Yeah, so it tends to be, so most cases, the exact time-dependent potential energy surfaces looks kind of more smooth, like less variable than the weighted polaritonic, right? Except look here, it looks like we're not smoothing, we smooth these things out, but then over here we get a big jump up. And I think what's happening here is that actually it's in a region where you sort of have a mixed character, and the system needs to know how to reflect. So basically this feature is, which is appearing here, is kind of a barrier that's kind of reflecting. This is when this part of the wave packet begins to reflect. So the role of these sort of step-like characters, one is kind of a velocity adjustment when the energy through the wave packet, different parts of the wave packet doing different things, as you said, right? One surface to another is changing. And the other role, I think, is also to, when you have a mixed character, to be able to reflect the part of the, as a correlation effect, like where you want to reflect part of the wave packet associated with one surface, but not the other. And so this kind of, puts up a little barrier. So yeah, we're still, this part we haven't written up yet, actually. We hope to soon. But,
thank you, that's very interesting. Thank you.
Okay, thanks, yeah.
Okay, so let's put an end to today's webinar. Thank you, Professor Maitra, for your interesting talk. And we really appreciate your contribution to the webinar. And yeah, so before we leave the meeting, I would like to make an announcement for next webinar. So, sorry. So on June 10th, next Wednesday, still at 9 a.m. PST, we'll have Professor Javier Azupuro to give us a talk entitled Addressing Atomic Scale Resolution and Nonlinear Effect in Plasma-Enhanced Molecular Spectroscopy. And don't forget to register. We'll also send out reminder emails as usual. Okay, thank you all for attending. Let's meet next Wednesday. Okay. Bye-bye.